Hello, everyone. This is our dry lab for the third week, and it should be our last dry lab. Hopefully, everybody's starting to get their kit. We'll try to start working from the kit next week. What this lab entails is enumeration of bacteria. It's quantitative microbiology. And I've uploaded a PowerPoint that goes through a diverse set of problems, okay? And you're welcome to look at the problems through the PowerPoint and kind of teach yourself if you choose to. But the way that you're going to be evaluated this week is that you're going to get a a quiz almost identical to this one. Consists of 5 questions. That's it. The questions are going to be almost identical. The only difference is that the numbers are going to be different, okay? So my intent is to go through over the questions of this quiz and help you prepare in passing this assessment on enumeration of bacteria. So the big picture here is that somebody hands you a vial, a test tube of microorganisms, and your job is to calculate the concentration of these microorganisms. How many colony-forming units per milliliter are there in the original cell density? Okay, that is the goal here. And so we start with some pedantic parts here. So our first problem teaches us about dilutions, what a dilution is. And it's not a complicated concept. If you take 1 milliliter of cells and you mix it into 9 milliliters of broth, you have turned that 1 milliliter into 10 milliliters. It's a 10x dilution. You have diluted it by 10 times. And the way that we say that scientifically is that it is a 10 to the negative first, because we're dividing 1 milliliter, what we started with, by 10 milliliters, what we ended up with, and that is 0.1 on your calculator, or 10 to a negative first if you use exponentials. So here, let's see if I can do this with Equation Writer so you guys can see what I'm doing. So it says, how would you produce a 10 to a negative third dilution from 1.5 milliliters of concentrated cells using the full 1.5 ml volume? Well, here's your dilution equation. And it's telling us that the dilution is the initial volume divided by the final volume, okay? So what does this mean? This means that we want a dilution of 10 to a negative third, okay? So we're going to call that 10 to a negative third, okay? And that dilution is supposed to be equal to the initial volume, which is 1.5 mLs, divided by some unknown quantity, final volume that we don't know. Okay, we're going to call that V2. So there we go, V2. Oops, let's use a big V. Big V. Okay, so now we need to find what V2 is, okay? I'm going to use an arrow. Arrows in logic means implies, okay? So this implies that V2, okay, is equal to what? Well, we're solving it algebraically. You would multiply both sides by V2, and we'll put in a numerator over here, and then you divide this side by 10 to the negative third. So once you do your basic algebra, it would look like this. 1.5 mLs divided by 10 to the negative third. Okay. Now, with exponentials, okay, when you have an exponent in the denominator and you want to bring it up to the numerator, the sign in the exponent changes. So this is equal to 1.5 times 10. Let's see if I can do basic math. Times. Where's my times? Oh, I can't find it. There it is. Times 10 to the third mLs. Okay. Notice that instead of having a -3, now I have a +3 because the exponent went to the numerator. Okay. What does this equal? Well, this is 1.5, and that 10 to the third means that we move the decimal point to the right 3 times. So this is actually equal to 1. We're going to move it 1, 2, 3 times. So it's 1,500 milliliters. Okay. Now what? Well, that initial 1.5 is part of that final volume. Okay. So we subtract 1.5 mLs. And I'm going to use my handy dandy calculator here because I don't want to do basic math apparently. And subtract 1.5, and I come out with 1,498.5 mLs. So what does this mean? This means that if I take my 1.5 mLs of cells and I add it to 1,498.5 milliliters of diluents or broth, okay, I would end up with a final volume of 1,500 milliliters. And that 1,500 milliliters would be a 10 to the -3rd dilution. So your answer is what? Your answer is that you would add 1.5 milliliters of cells, just like the author asks, to a total diluents of 1,498.5 milliliters, to yield a final volume of 1,500 milliliters. And in doing so, you would have turned that 1.5 divided by 1,500 into a 10 to the -3rd dilution. And that's the answer to the first problem. Okay? All right, let us continue. Let's look to the second problem here. It's another dilution problem, but this time what the author is trying to bring home is errors in dilution. And in the clinical environment, a lot of you are going to become nurses. In the clinical environment, this is a big problem. There's even a term for it. It's called death by decimal. This happens when there's an error of 1 order of magnitude or 10 times in the dilution of a medication, and you end up either under-medicating or over-medicating somebody severely, which can cost them their lives, okay? So here it says, you were instructed to add 1 milliliter out of 5 milliliters of undiluted sample to 99 milliliters of sterile diluents. Instead, you added all 5 milliliters to 99 milliliters. What is the intended dilution factor? And what was the actual dilution factor? And this happens to me in my lab all the time. I try to tell my lab my lab assistants how to do a dilution, and somehow they get their wires crossed and they end up making the wrong dilution. So this happens to me all the time. So it's a dilution. So we're going to use the same equation. Okay. So using good old equation writer here, we're going to say that the dilution is going to be equal to what? It's going to be equal to the initial volume, which is supposed to be 1 milliliter, so that's 1.0 ml. Okay. And we're going to divide that by the final volume. Well, the final volume was supposed to be 1 milliliter plus 99 milliliters, which make it 100 milliliters. Okay. So what I'm going to do is the author wants us to distinguish between the intended and the actual. So I'm going to put a little subscript on this D and call it the the I, the intended dilution factor, because this is what we're trying to achieve. We didn't achieve it. That's what we're trying to achieve. Notice that the milliliters cancel. Okay, so milliliters in the top and milliliters in the bottom cancel, and that makes sense because a dilution is really a pure number. Okay, so now what? Well, that's equal to what we're going to do now is we're going to put this in exponential form. Okay, so we're going to go over here and we're going to say it's 1, an exponential. If you don't know this, 1 is 10 to the 0. And that's because in math, any number raised to the 0 power is equal to 1. 100, well, 100 is 10 to the 2nd power. Okay, why? Because 10 times 10, which is 10 squared, is equal to 100. Now what do? Now we carry out the exponential calculation. And remember, if you're dividing, it is the top exponent, which is 0, minus the bottom exponent, which is a 2. So the dilution factor here is 10. 0 minus 2 is a negative 2. So that's a 10 to a negative 2 dilution. That is the intended dilution. Okay. Now, this is what I love about computers. You can copy and paste. So I'm going to copy. Right underneath it, I'm going to paste the actual dilution. So this is my actual. This is what actually happened. There we go. So what did the student actually do? Well, instead of adding 1 milliliter to 99, they added 5 milliliters. So the initial volume was at 1 milliliter. It was 5 milliliters. And the final volume was at 100 because they added 5 to 99. So the final volume is 99 plus 5, which is 104. See what a mess that is? Now I can't even use really exponents very well here. This would be 5 times, actually I can, where can I steal that from? I'll steal it from right here. 5 times, boom, 5 times 10 to 0, that's the same as 5 times 1. And then over here, this would be approximately 1. This would be approximately 1 times 10 to the 2nd. So in other words, this doesn't change very much. Okay. So what do we have? Well, this is now going to be approximately equal to, let's do an approximately equal to, boom. 5 divided by 1, that's going to be a 5 times 10 to the negative 2nd. Okay. I'm going to put that 1.04 over here, if that makes you feel better. Okay. But it's not going to change anything. 1.04 times there. That is equal to that, and this is equal to that. But if you take 5 and you divide by 1.04, you come out with 4.8, which is very, very close to 5. So nothing changed. So we can leave the 5 on there and come out with a very acceptable answer. So this is what it should have been. It should have been a 10 to the negative 2nd dilution. But the actual dilution came out to be a 5 times 10 to the negative 2nd dilution. So that's kind of a big mistake by whoever was doing this dilution. Okay. Okay, so I'm going to bold those 2 answers to emphasize the fact that that's what the answer is supposed to be. And we're going to move to the next problem, problem 3. It says plating 0.5 milliliters of a sample diluted by a factor of 10 to the negative 6 produced 57 colonies. What was the original concentration of the sample? Okay. Here is our formula right here. Okay. And the way that this works is that the original cell density is equal to the number of colony forming units that you have on your plate divided by the volume, by the dilution factor that was delivered on that plate. And if we're doing a wet lab, the thing that we have to take into account is that that plate with the colony forming units would have to be a countable plate, which means that it would have to have between 30 and 300 cells. Otherwise, we don't trust it. Okay. So let's do the calculation just to show you how easy this is. Okay. We're going to go ahead and insert equation writer again. And we're going to say that the original cell density, OCD, is equal to what? Well, it's equal to the number of colony forming units. How many colony forming units do we have? We have 57. And right away, we're going to start doing this in exponential form. So we're going to say that that's 5.7 times 10 to the first power. Hopefully that makes sense to me, to you. I mean, if I take 5.7 and I multiply by 10, I end up with 57. Okay. In the bottom, it is the dilution. We're going to divide by how much it was diluted and also what the volume plated is. Okay. So the volume plated, how much did we plate? We plated 0.5 mLs. So we're going to go ahead and put, our plated volume. What is that going to be? It's going to be 5 times 10 to the negative first. Because negative 1 means that we're going to move the decimal point to the left of ones, giving us 0.5, which is correct. Okay. What are the units on this? The units are milliliters, like so. On the top, I left some units out. That should be CFUs, colony forming units. Okay. In the denominator, we're going to multiply the volume plated by the dilution factor. Okay. So what's the dilution factor? The dilution factor was given to us as 10 to a negative 6. So we're going to say, okay, so that's 10 to a negative 6. There it is. So that's it. Now we just have to do basic math, okay? So in the numerator, everything remains the same. So I'm just going to copy everything over to the right. There it is. In the denominator, it changes a little bit. This is going to be 5 times 10 to the what? Well, again, with exponents, if you're multiplying them, and we are, and the bases are the same, you add the exponent. So you have a negative 1. Let me make this bigger so you can see it. You have a negative 1 and a negative 6. That makes this a negative 7. Okay? All right, we're almost, oh, let's not forget our units. Still milliliters. And now we'll do our calculations. 5.7 divided by 5, suspiciously close to 1. Even if you take your calculator, right? 5.7 divided by 5, 1.114. 1, close enough, okay? 1 times 10 to the what? Well, it's a 1, and now we're going to subtract the exponent on the denominator, so that's 1 minus a negative 7. So 1 minus a negative 7, that's 1 plus 7, and that makes this an 8. And that's going to be CFUs per milliliter, okay? Colony forming units per milliliter, and that is your original cell density that we calculated. Okay. All right, let's continue. Now we have a problem where it's asking you volumes in microliters. And I include this intentionally because I have found out that my students do not have a lot of experience dealing with milliliters and microliters in particular. Other than that, everything else is the same. Okay. So it says you have inoculated 200 microliters of a sample diluted by 10 to the negative fifth on a neutron agar plate after incubation. You count 72 colonies. What is the original cell density? So really, we're going to use the exact same equation. Nothing has changed. Okay. As a matter of fact, I think I'm going to steal this from up here. And let's see. So at the top, we have the number of colony forming units. The number of colony forming units was 72. So I'm going to say this is 7.2 times 10 to the first colony forming units. And then in the denominator, I'm going to have the volume plated. So my volume plated is 200 microliters. Okay. So I'm going to go 200 microliters. Let's see if I can insert a microliter in there. Symbol. Oh, there it is. Look at that. That's nice to know. Microliter. Okay. And then what I'm going to do is I'm going to multiply that by the dilution factor. Okay. My dilution factor is 10 to the negative fifth. So this is going to be times 10 to the negative fifth. And that should be it. Everything else is garbage. So here's my volume plated. Here's my dilution factor. Okay. Now the thing is that original cell density typically gets reported in colony forming units per milliliter. And over here I have a microliter. See, so what's the explanation? Well, 1 microliter is equal to 1 millionth of a liter. So that's equal to 10 to the negative 6. So that's 1 millionth. Okay. By contrast, a milliliter is 1,000th of a liter. Okay, so that's 10 to the negative third. That's a milliliter. Okay, what does this mean? Oh, I'm going to get rid of my formatting. What does this mean? This means that there is 1,000 microliters in 1 milliliter. Okay. So there's 1,000. Oops, let's try it again. 1,000 microliters, because if you multiply this by 1,000, 1,000 is 10 to the third. So 10 to the negative 6 plus 10 to the third gives you a 10 to the negative 6. So there's 1,000 microliters in 1 liter. Oops. In 1 milliliter. That's what I meant to say. That's our conversion factor. Okay. So right here, we have to multiply. We have to multiply by the fact that 1,000 microliters, let's see if I can steal the microliter from here. There it is. That 1,000 microliters is 1 milliliter. But remember, we don't do ones, right? Because we're working in exponents. So we're really going to do 10 to the 0. 10 to the 0 milliliters. Okay, we're doing okay. I should probably use a capital L here so nobody gets confused. There it is. The microliters cancel. So that microliter, I'm trying. That microliter and that microliter cancel. There they are, they're gone. So we're going to divide 200 by 1,000. Okay. So what I'm going to do is I'm going to copy all this stuff here. I'm going to put it over here. And 200 divided by 1,000 divided by 10 divided by 100 divided by 1,000 is 0.2. Okay. Okay. So 200 divided by 1,000 is 0.2. So we can go 0.2. The microliters cancel. The 1,000 in the denominator disappears because we already divided by it. Okay. So the only thing that remains is this 10 to the 0. We're going to say times. We're going to say times. Oh, I want to put it right here. 10 to the 0. And then right there we're going to go times. Okay. So at 10 to the 0, milliliters stayed. And then the 200 divided by 1,000 became this 0.200. All right. Let's keep on going. Let's put this over here. And we need to put an equal sign there. All right. Now I need to turn this into an exponential of some sort. Okay. So that 2, what does that equal to? Well, that's actually 2 times 10 to the negative first. So I'm going to write that as a 2. Let's see, 2 times 10 to the negative first. If you notice, the my decimal point would be right here, but if I move it 1 to the left, I end up with 0.2. So 2 times 10 to the negative first and 0.2 mean the same thing. Okay. Now we can go ahead and start doing some of this multiplication. All right. So I'm going to grab this guy again. I'm going to copy it down here. And I'm going over extra steps to make sure that nobody gets confused on what we're doing here. Okay. So now we're going to have equals. We're going to have our quotient. Okay. In the top, nothing changes yet because everything that's happening is happening on the bottom. So we're going to leave the top the same. But on the bottom, we have a 2. That's all we have is a 2. And then we're going to multiply that by all the exponents. Here we have 1 exponent, 2 exponents, 3 exponents. They're all being multiplied. The base is going to be 10. So we're going to put a base of 10. And then we're going to add the exponents. We have a -1 plus a 0 plus a -5. So -1 plus 0 is -1. -5 is a -6. So it's going to be a -6. And the units are going to be milliliters. Okay. Now we're going to say that that's approximately equal to 7.2 divided by 2. What is that, about 3.5, 3.6? 3.6. 3.6 times 10 to what? Well, this is going to be a 1. And remember, we subtracted denominators, so it's going to be 1 minus a -6, which is the same as a 1 plus 6. 1 plus 6 is 7, so that's 10 to the 7th, and the units are going to be colony-forming units per milliliter. And that's our answer. Okay? So the one hiccup in this entire problem is the fact that instead of starting with a delivered volume in milliliters, we delivered it in microliters. Okay, so because of that, we had to turn the microliters into milliliters. Here it is, and then we had to do the math out.